Hello and welcome to the logic of it all. In this video, we'll begin exploring sets, one of the most fundamental ideas in discrete mathematics. What we are studying here is usually called naive set theory, which is a simple practical version of set theory that works very well for most purposes. There are also more rigorous and axiomatic versions of set theory because naive set theory can run into problems. One famous example of such problems is called Russell's paradox. Here I'm just mentioning this, but there will be another video where I will talk about Russell's paradox in more detail. For now, let's focus on this practical and simple version of set theory, which is good enough for our intents and purposes. So first of all, we should start by explaining what a set is. Okay, and a set is a collection of well-defined objects that are called the elements or the members of that set. Here the emphasis and the focus is on well-defined, which means there shouldn't be any ambiguity about whether or not an object belongs to a set. To clarify that, let's take a look at a couple of examples. First question. If we consider the collection of all positive integers that are less than 10, is that a set? And if you think about it, there is no ambiguity about the membership here. The elements are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. And everyone agrees on that. So because of that, because there is no ambiguity or because it's well defined, this will be considered as a set. On the other hand, if we consider the collection of all delicious food, you can see that here there is ambiguity about which food is or is not delicious. It's subjective. And because of that, this is not considered a set. In the next step, now we want to learn how we can represent a set. And here I'm going to show you two different ways of defining or representing a set. The first one is called listing method or roster form. Here, very simply, we just list all the elements of the set, all the members. We separate them by commas, and then we put them in braces. So for example, if we are thinking about the set of positive integers that are less than 7, 1, 2, 3, 4, 5, 6, separated by commas, and put in braces. Very simple. Now, a couple of very important properties that we are going to revisit a little bit later as well about sets and their members. The first one is, since a set is defined only by its members, what belongs or doesn't belong to the set, the order of the elements is not important. So if I say the set containing 1, 2, 3, 4, or 4, 3, 2, 1, or 4, 3, 1, 2, these are all the same set. Okay, so the order of the elements is not important, or it doesn't matter. Secondly, repetition doesn't matter either. So if you repeat an element like 5 in this example twice or 3 times or once, these are all the same set. So the set containing 5, 1, 5 is the same as the set containing 5 and 1. So you can get rid of the repetitions because they are not important in the context of sets. Now, I told you we are going to see two different methods for representing or defining a set. The second one is called set comprehension or the set builder notation. So if you think about it, if your set has a few elements, a finite number of elements, it's easy to use the listing method when you write all the elements and separate them by commas and so on. But as soon as your set has a larger number of elements, maybe 1,000, for example, then you can see that this method is not practical. And even more importantly, we will see sets that have infinitely many elements. The set of numbers, integers that are greater than 7, 8, 9, 10, 11, 12, and so on. So and so on means it's infinite. So you cannot write all the elements down. So this second method is particularly useful in these scenarios. So what we do here is that instead of listing all the elements, we write down the property that the elements of that set must have. Okay? So for example, we can write A, which is the name of the set, is equal to the set of all x's, as you can see here, such that X is an odd number between 6 and 12. Okay, so this is called set comprehension. We are describing the properties that the elements of the set must satisfy. They must be odd and they must be between 6 and 12. Okay, now in this case, this is a small enough set that we could actually use the listing method, and you can see that odd numbers between 6 and 12, we have 7, 9, and 11. So A is actually the set 7, 9, and 11. But this first method is called the set comprehension or set builder notation, and this is the one that we saw in the previous slide, which is the roster form. Here's another example, and I want you to pause the video here and think about this yourself for a second. Okay, so B is the second set that we are introducing here, is the set of all Z such that Z is a positive even number less than 12. Okay, so if you want to write this set using the roster form, how would it look like? And you can see that positive even numbers less than 12, they start from 2 and 4 and 6, 8, 10, and that's our set B. Now, since members of the set are the most important things about them, we need an operator to say whether something belongs to a set, is a member of a set or not. And we use this symbol of epsilon to represent that. So if X is an element of the set, we say X belongs or is an element of A. So belongs to A or an element of A. So for example, we can say that 7 is an element of the set 310279. And if it is not the case that X is an element of the set A, then we put a line through the membership operator and we say X does not belong to A, or X is not an element of A. An example of that would be 7 is not an element of, and here I use set comprehension. As you can see, my set is the set of X's where X is a positive even number less than 10. So if you think about that, positive even number less than 10, what are they? 2, 4, 6, and 8. And obviously 7 does not belong to that set. So 7 is not a member of that set. Now, for practice, I'm going to show you some more examples. Again, I want you to pause the video, think about the answer, and then look at the actual answer. So the first statement is 12 is an element of that set. Is it true or false? And obviously you can see that 12 does not belong to that set, so that's false. Here's another statement. 7 belongs to the set of X's such that X is odd and X is less than 6. Again, you can see that this is a false statement. And here's another one. 12 does not belong to the set 1, 2, 7, 13. And that's a true statement because 12 actually doesn't belong to that set. Right. Now, there are two special cases for the sets, namely the smallest set that you can imagine, which is called the empty set, which is basically the set that contains no elements, a set without any elements. Now, we can represent that set either by doing this. So we open the bracket, there are no elements to be listed, and then we immediately close it. So that's one way to represent the empty set. Or we can use the Greek letter phi to represent the empty set. As an example, if we use set comprehension and say the set of X's such that X is between 10 and 12 and it's even, you can see that there is no even number between 10 and 12. So as a result, this set is going to be a set with no elements, or the empty set. Now, here's a question for you. Is it true or false to say X belongs to the empty set? And we don't know what X is. So replace X with anything that you like. And the answer is, this is false, because no matter what X is, it cannot belong to the empty set because by definition, the empty set doesn't have any elements. And the other special set that we have is kind of like the opposite of the empty set. It's called the universal set. And again, for technical reasons, we don't have one universal set that works in all contexts. So it depends on the context. So a good way to think about a universal set is, depending on the context that you have, it's a set that contains all the elements under consideration in that particular context. Okay, and we represent the universal set with the letter U. For example, if you're talking about the students at the University of X, then the set of all students in that university can be the universal set. Or if you are talking about integers, positive integers, then the universal set could be 1, 2, 3, 4, 5, and so on. So you see that depending on the context, your universal set can be different.